is Robert Mann, and I'm the chair of the Pascal Lectures Committee. In your program here, you can see the names of the other members of the committee, as well as a little bit of background about Blaise Pascal, for whom these lectures are named. He was a 17th century French academic and a very committed Christian. He was a forerunner of Newton in the establishment of calculus and is well known both for his Pensées and for the now famous Pascal's wager that economists like to discuss in considerable detail depending on their moods. This year's lectures are sponsored by the Reed Trust Foundation in part. The Reed Trust is named after Priscilla and Stanford Reed, who believed very much in the engagement of academic life and thought with Christian theology, and the Pascal Lectures Committee at Waterloo gratefully acknowledges their sponsorship, as we do also gratefully acknowledge the many others who have privately donated that makes this lecture series possible. One request is that no BlackBerries or cell phones be turned on during this talk, so please shut your machines, your portable communication devices off during this talk. I would also like to remind you that after the talk tonight, there are cookies and juice, or there will be cookies and juice outside for the possibility of allowing further discussion and conversation amongst those of us here this evening. I'm very pleased to welcome again for the second of two lectures Dr. Jennifer Wiseman. Jennifer is an internationally renowned astronomer who very early in her career discovered a comet when she was a senior undergrad, now known as the comet Wiseman-Skift, after the Wiseman that found it on the photographic plates that were taken by Skift, as I understand it. And this was an astronomical object never seen before. I understand it has roughly a 6.5-year period about the Sun. But she has since moved on to do a variety of things, both in research in astronomy as well as in science policy in the United States. As you can see from her bio, I've known her personally for a number of years. She is currently the Vice President of the American Scientific Affiliation, a fellowship of Christians in the United States that also are scientists of all professions. She will become the president of that organization beginning in, I think, about 2 months. There's a number of things you can read about her in the bio. I thought I would just add to this to say that Jennifer herself has never been in space, but she's come a whole lot closer than I ever have, and that probably most of us ever will, in that she had the opportunity to ride one of the planes that NASA uses so that astronauts can experience weightlessness. And what this plane does is it flies very, very, very high up in the atmosphere and then all of a sudden just drops in what is called free fall, at which point everything in the, as it's just falling toward the Earth, everything inside just floats around for a period of on the order of 45 seconds, and one gets to experience weightlessness, and she has had this opportunity. Of course, you don't want it to keep falling indefinitely for obvious reasons, so NASA, after it's fallen for a while, the pilot has to then accelerate the ship back up, and you experience a force of gravity that's twice as powerful as on the Earth, and then you go up and you do it again, and you do it again, and you do it about, 40 times, some odd, like that. Needless to say, medication is generally taken by those that ride this thing, and the name of this plane is called the Vomit Comet. So Jennifer has also participated in working with astronauts in an underwater testing tank. She is a scuba diver by avocation, and so she has participated to some extent with astronaut training in the tanks that also simulate weightlessness. at NASA. And she's done a number of interesting things that I'm sure you like to hear about. So please welcome this year's Pascal Lecturer and rider of the Vomit Comet, Jennifer Wiseman.
Thank you. I'm really delighted to join you again for the second evening of the Pascal Lectures. This evening, I want to explore a little bit more in the direction of what we touched on last night, for those of you who were there, and also this morning, for those of you who were there, which is the fact that we are discovering planets around other stars now. This is the stuff of science fiction for many, many years, and now suddenly it's not fiction anymore. We are actually starting to find planets orbiting other stars. There are other solar systems out there. What does that mean? What are we about to find? What will it mean for our understanding of humanity if we are to find not only other planets, but the potentiality for other life? Let's explore that together just a little bit. I want to show you a little bit of what I showed last night by popular demand by people who weren't able to see last night's lecture, to show you the context in the universe. Oh, that's better. I don't know if that messes up the tape or not. Well, we're going to see the planets in context of where they exist in our universe. What you're seeing on the screen right now is a galaxy. It's called a barred spiral galaxy, which means it is a flattened collection of stars and gas. It has several spiral arms, and as you can see, it's also got a bar-like structure in the core. That's common for many of these spiral galaxies. The glow in the center is simply the combination of countless stars and a high-density arrangement there in the core. The starlight all blends together. The bright spots throughout the arms indicate regions where young clusters of stars are forming and ionizing their surrounding gas and lighting it up. Spiral galaxies are very active places where stars are continuing to form. I want us to kind of stoke our questioning minds tonight. You may have been thinking about all kinds of other things today, like, why did I move to Canada when it's so cold up here? Or, I have so much work to do. Is it even possible that I should go to some lecture tonight? Or how do I park the car? Or all those kinds of things. Let's think bigger this evening. Some of the questions that we explored last night are, how big is the universe and how old is it? What's going on in the universe? What are we discovering in astronomy? And eventually, are we going to find other universes, or what would it mean if there were other universes? But the questions in bold here are the ones we didn't get to talk too much about last night, which is, how did we get here, and what is the origin of life? Are there planets around other stars? And if so, could we ever visit them? Mind you, I'm not going to address all these questions tonight, but I just want to get you thinking. And could there be life on these other planets? And if there's life, could there be intelligent life? And if there's intelligent life, could they be as stupid as we are? Would they have, wars and good and evil? And would they create stupid sitcoms for television? And would they, what would they be like? Would they have any belief in God? Would they have some sort of religious belief? What would these beings be like? We've seen a lot of science fiction, which can take us through many of these things without us even thinking about it, but we need to think a little bit. And then also this brings to mind, if we find life elsewhere, what does that do in terms of our understanding of human significance? Does this elevate or bring down our comprehension of the significance of life in the universe, and in particular our lives? What does it mean for us? And in the context of these lectures, these are the lectures on Christianity and the university. What does it mean in terms of Christian faith? Let's look at some of these things tonight together. I'd like us to do a little overview of the universe and then talk a little bit about how we are actually finding extrasolar planets these days, and then go into the discussions of significance. Do a time check here. Okay. I want to remind you that you can see some of these images anytime you want by going to a wonderful website called Hubble Site. It's hubblesite.org. You can see it right there on the screen. And if you click on the gallery there, you can find a countless number of Hubble Space Telescope images of galaxies, stars, planets, anything you want, with explanations, and they're in all different kinds of resolutions, so you can pull it down and make it your wallpaper or print it out or just enjoy looking at it. Also, tonight's discussion on exoplanets. An exoplanet is a planet outside of our solar system. NASA has a whole exoplanet exploration program now because it's a hot topic. And you can learn all about that at the website on the screen here, planetquest.jpl.nasa.gov. All right, where do planets fit into the universe? Let's do a little overview. This is our friend, the Hubble Space Telescope. It is in orbit around the Earth, whipping around about once every 90 minutes. It's above the clouds, as you can see in the picture here, so that it can get crisp, clear images of space without the interference of clouds in the atmosphere. So some of these pictures are taken with Hubble. Pardon me for those of you who've seen some of these pictures. This is for the benefit of those who, for some unfortunate reason, missed last night's lecture. So this is one of many star clusters in our own galaxy, the Sagittarius star cloud, and I pointed it out last night to give you a sense of the beauty of stars. You can see the different colors in this particular cluster and the different brightnesses of stars, reds and greens. Now, this projector doesn't show the brightness of the reds as it does on my screen, so that's unfortunate. But it is a beautiful cluster of stars. There are many, many stars in our galaxy. In fact, there are hundreds of billions of stars in our one galaxy. We believe we are in a spiral galaxy, and there are billions of galaxies. In fact, if you don't remember your Astronomy 101, just to remind you that our sun is a star, it's the nearest one. Our Earth is a planet that orbits the sun, along with the other planets in our solar system, but now we know there are planets around other stars. In fact, there are billions of stars in our Milky Way galaxy of all different ages. There are old stars in the galaxy that are starting to end their ability to fuse hydrogen into helium, creating the starlight that we see. And eventually those old stars spew out their outer atmospheres, and if they are large enough stars, they will actually explode into supernovae. In both cases, they are ejecting the material, the products of the fusion inside the star get ejected into the interstellar medium and go into the production of the next generation of stars. So it's a very dynamic process where subsequent generations of stars get built using the gas, in large part, that's ejected from previous generations of stars. So you get heavier and heavier elements the longer the universe exists. And that's good for us, because in our star system, we have heavier elements, such as carbon and iron, that did not exist in the early universe. It's taken several generations of stars to get what we enjoy and need to have a planet and have life. Our galaxy contains this variety of stars, but now we know there are actually billions of other galaxies, hundreds of billions of galaxies, many of them looking like these spiral structured shapes that I showed you, some of them in different shapes, some of them more spherical in shape. And we didn't even know this until a few decades ago. So we're at a very privileged time in human history to get to understand the enormous magnitude of activity and content of our universe. Here's a galaxy I showed last night, this beautiful, beautiful symmetric galaxy, a spiral that also shows in the background some absolutely gorgeous background galaxies that just are the background noise in this picture, but you see spiral structures of all kinds and even highly reddened galaxies that are in the very distant universe in the background of this picture. In fact, here's a little slice of those billions of galaxies as I showed last night. These little spots of light are not stars. They're each a galaxy, each with billions of stars. And this is simply one pencil beam direction in the sky. If you imagine this extrapolated over the full sky, you get some sense of how enormous the universe is. If you imagine each of these having hundreds of billions of stars, and each one of these stars potentially having a planetary system around it, it's kind of mind-boggling, shall we say. And in fact, as we look through the history of time, this is another chart I showed last night. So this is your review from last night. From left to right, we sort of see this as the beginning of the universe to where we are on the right side. WMAP is the name of a particular telescope. But any telescope or any of us looking out in space would be looking from our time back through space, seeing both nearby objects and distant objects at the same time. But the distant objects, we're seeing them as they were back in time when they emitted their light. So we have to differentiate between the nearby objects that are near to us in space and time, and the more distant objects which are appearing as they did when they emitted their light, sometimes billions of years ago. We're looking back in time. Now, as galaxies developed over time, they were able to form stars, generations of stars with heavier and heavier elements, and the later generations of stars would form debris disks, so this heavier material around them as they form. We see that now, and I'll show you pictures of that. And it's out of those debris disks, rocky disks of dust and later larger rocks, that we believe planets form. They form when these pieces gravitationally stick together. And that only happens more in the near part of history, where we had the heavier elements to do that. So we're going to look in our own galaxy and see if we can find planets. Here's what we think our galaxy looks like, something like this, but we can't get outside of our own galaxy to look at it. And you'll see how a galaxy is filled with gas and dust. You can even see it in this picture. It's in these gaseous regions where you get pockets of collapsing material that can form stars and planetary systems around them. And it's a very active and ongoing process. We're seeing different stages of these things all at once as we look around our own galactic neighborhood. For example, the Orion Nebula that we looked at last night. As you peer into the stars in this constellation, you will see a nebula where stars are forming. And the new stars that have completely formed are bright enough to ionize their surrounding gas to create beautiful colors, which on my screen look red and orange, and on this screen look green and blue. Isn't that amazing? So I don't know why we don't get a color translation correctly. The older stars, as I mentioned, will expel their outer atmospheres into the surrounding medium, enabling the next generation of stars to take advantage of all the production that's gone on in that star throughout its life. This is a remnant of an old star that's exploded. We call it the Crab Nebula. There are about 200 billion stars in our galaxy. This is an image toward the center of our galaxy, and it's just filled with stars, just absolutely filled with stars. If one of them is our sun, one star, and we know that that sun has planets and one planet has life, is it possible, just possible, that we could find other stars with planets and even an Earth-like planet out there? That's where we want to go tonight. This is Earth, by the way, if you haven't recognized. So what exactly are exoplanets, and how do we find and how do we study them? This is a topic near and dear to my heart because I work at a NASA facility, a NASA center near Washington, D.C. called Goddard Space Flight Center. And at Goddard, we focus on science missions such as the Hubble Space Telescope and other space telescopes, and also satellite telescopes that are looking down at the Earth to study climate and oceans and weather patterns, things like that. My laboratory is in the Astrophysics Division of Goddard, and I'm the head of this lab, and it's called the Laboratory for Exoplanets and Stellar Astrophysics. So the stellar astrophysics is anything about stars, studying stars, and the exoplanets is studying these planets around other stars. Now, this is very interesting because when I was in graduate school, I graduated about 15 years ago with my graduate degree, and extrasolar planets were a very new thing. They were just on the verge of starting to be discovered in the ones and twosies kind of thing, and it wasn't taken as a serious part of astronomy yet. And now, 15 years later, it's very central, and every university and every NASA center and centers here in Canada want to study exoplanets. It's a hot topic. We're finding them. We want to know how they form. We want to know if they have atmospheres, what they look like. It's a very, very rapidly developing field. An extrasolar planet or an exoplanet is a planet beyond our solar system that's orbiting a star other than our sun. And over 300 planets have recently been detected orbiting other stars. Now we're actually at about 400. This is just happening very rapidly. And most of these detections are indirect, which I will show you what that means. The planets we are able to detect are not yet Earth-like in terms of being as small as Earth and terrestrial and in a nice habitable zone around their star. because our telescopes are not quite sensitive yet. But we are working very hard on the technology to get that sensitivity and those capabilities that we will need probably within the next 10 to 20 years to really start surveying the neighborhood for planets like Earth. What about these distant worlds? Are we the first ones to actually think about this? Well, the answer is no. Thousands of years ago, Greek philosophers were also speculating about this possibility. They didn't quite understand how the cosmos was structured. At that time, we had in most ideas, we had an Earth-centered cosmos. But nevertheless, there were philosophers, such as the Epicurean philosophy. Epicurus wrote that there are infinite worlds, both like and unlike this world of ours. We must believe that in all worlds there are living creatures and planets and other things that we see in this world. And even Giordano Bruno in medieval times thought about this and proclaimed that there are countless suns and countless Earths all rotating about their suns in exactly the same way as the 7 planets that they knew at that time of our system. The countless worlds in the universe are no worse and no less inhabited than our Earth. Pretty forward thinking for that time. We're still trying to figure out if that could be possible today. Now, this guy was burned at the stake, but I don't think it was for this statement in particular. But so you have to be a little careful about where you do your musings. So, and then of course we all have many experiences of Hollywood telling us what we ought to think that extraterrestrial life would look like and do. So it's sort of hard actually to get that out of your mind and try to start from scratch about what is it that we're actually seeing, and what would we do if we actually greeted an alien culture. All right, how do we detect exoplanets? This is the next few charts are my technical part of the presentation, so hopefully you'll walk away from this having learned a little bit of the science and the technical approaches that we take to looking for exoplanets. We look for, in many cases, tugging motions on a star. Now, why don't we just look at the planet? Well, these planets are extremely dim and small next to something extremely bright, a star. In fact, Earth-like planets would be 10 orders of magnitude dimmer than the star if it's a sun-like star that they're next to. And we're not quite yet capable to pull something that dim out of the glare of something that bright. It's a really difficult technical problem. But clever people have figured out indirect ways, like detectives, of finding out the presence of planets without actually necessarily seeing those planets. And the most successful way so far, by far, is what we call the motion technique. In most cases, it's the radial velocity technique. We see the star wobbling back and forth in the sky toward us and away from us. That wobble is caused when the planet around it exerts a gravitational tug on the star, just as the star is exerting a gravitational tug on the planet. That's one way of finding a planet. Another way is looking for transits when the planet, if you're happening to see a system where the planet is orbiting in such a way that it passes in front of the star as you're looking at the star. Every time it transits around in front of that star, you'll see the starlight dimming periodically. You can find transiting planets that way. And then finally, taking an image of the exoplanet is what we would really like to do, but as I mentioned, that's difficult to do. Here's a picture of what a wobbling star might look like if you measured that wobble in the plane of the sky. This is an example of what we would call astrometry, which is measuring the motion of star in the plane of the sky. And by carefully calculating what that motion is, you can figure out what kind of object must be causing that motion. So we can find it this way. You can also find it in the direction of your line of sight, the wobbling in the radial direction, by looking at the shifting of the light back and forth as it comes toward and away from you. This is the technique that is the most popular right now. Who's doing this? Well, some of this is done by excellent ground-based telescopes. You don't necessarily need to go into space to do this radial velocity technique of finding wobbling stars. Down here on the lower picture on the left is Jeff Marcy. He's a very famous planet finder. He's found hundreds, probably hundreds of the 400 he and his team have found using ground-based telescopes. So here's how it works. Here's our scientists looking at this happy star. And the happy star, as it's moving away because of some unseen planet, that light gets kind of stretched out on its in terms of what the scientist sees because of the motion, the relative motion of the star from the observer. So it actually looks redder to the observer than it was when it was emitted. And likewise, when the star is moving back toward the observer, that light appears bluer. This is called redshifting and blue shifting of light due to objects in relative motion to one another. So if you see this happening on a periodic basis, you can determine that there is something going on in terms of regular orbital motion around that star. Now, what we're actually looking at is our particular frequencies of light that would be emitted by that star so that you can track the motion of those particular frequencies. And the most popular, of course, is hydrogen. Hydrogen emits at very precise frequencies. You can see very specific lines as you stretch the light out in a prismatic way with a spectrograph. And as you see that pattern of lines suddenly get shifted a little bit to the red or a little bit toward the blue, you can discern what it is that's causing that starlight to become redshifted and blue shifted due to the motion of the star. So there's our happy star. And there's another picture of what that kind of looks like if you have an unseen planet orbiting the star. They're actually both orbiting what's called the center of mass between the two objects. And if you have a very large object and a very small object, their mutual center of mass will be somewhere near the center of the large object, which just basically causes the large thing, in this case the star, to wobble, and the small thing to orbit around the other large object. So this is another picture of what it looks like to find stellar wobble due to Doppler shift. The goal, of course, is to find something like Earth. We want to find a planet that's Earth-like and that maybe could harbor life. That would be kind of one of the most profound scientific goals. But right now, the planets that we've found are not good candidates for this. They are big gas giant things like Jupiter and Saturn, because we're not generally capable of seeing anything too much smaller than that just yet. We're getting there. And often they are in the wrong location. They're either in a place that's too close to their parent star, so they're too hot, and all the liquid water, if there were any on that planet, would have evaporated away. Or they're too cold. Any liquid water, if it were a terrestrial planet and had liquid water, would be frozen. So many of them have either orbits that keep them too close or too far from the star, or are highly elliptical, so they drift in and out of a nice, comfortable zone. So many of these planets are just not right for what we're looking for. And in fact, as I mentioned, finding another Earth is not easy because Earth-like planets are small. They're relatively close to bright stars, and they're hard to see. So we're seeing things like Jupiter, or we're detecting things big like Jupiter, but we want to find things that are relatively small, like Earth. That's the technological challenge that we're facing. If you want to think of it like a lighthouse, stars are a billion or more times brighter, if you think of it as a lighthouse, than a firefly. Do you see the little firefly up there? So it's kind of like trying to see a firefly in the glare of a lighthouse. And that's not easy. So there's our firefly. Oops. And so that is one of the technical challenges that people in my lab are doing, is designing devices to put inside telescopes or out in front of telescopes that will block that light, that bright light, and enable us to see the dim light around it. It's not easy because light actually can refract around things, and so it's very hard to actually contain bright light so that you can see dim light around it. We're even developing concepts where you might put a star shade tens of thousands of kilometers in front of a telescope to block, align with the telescope, block the bright light, and so that the only thing that gets past that and makes it to the telescope is the light from a circumstellar planet in that system. And of course, we want to go one step farther and find out, what if we're not actually the only form of life out there? So one of our goals is to not only detect these exoplanets, but to characterize them. And by characterizing, that means finding out how massive they are and using the technology to actually do a spectral analysis of their atmosphere, spreading out the light, looking for these spectral lines in the spectrum that indicate the presence of things like oxygen or water or methane. Finding out if any of these planets are actually capable of supporting an atmosphere or supporting life. We, within our national space agencies and professional astronomers at universities, are mostly looking for primitive life forms. But there is an organization that's looking for the other end of the intelligence spectrum, which is looking for intelligent life, and that would be the SETI program, the Search for Extraterrestrial Intelligence, which is a privately funded program that is spending great effort to listen for signals from intelligent civilizations that are trying to reach out to us. And they are scanning the sky and trying to choose highly good candidate planets to aim their ears toward, to listen for signals. They haven't heard anything yet that sounds like an intelligent civilization, but they say they are just starting. They have many, many other frequencies and bandwidths to try, and so they're in it for the long haul. All right, how will we know if a planet supports life? Well, we'll look for evidence of oxygen. Again, looking in the spectrum, there's an example spectrum down there in the lower left. The light comes either from the planet or is reflected off the planet, and we look at what we see and try to find evidence of the chemistry on the planet. We want to look for liquid water because any life form that we know of on Earth depends to some degree on the ability of liquid water. And yes, there might be life forms out there that don't rely on liquid water, but we don't even know how to look for that. So we have to start with what we know. We have to find places where there is liquid water that would correlate most to the kind of life that we would recognize. We analyze the light from the planet, both the emitted light and the reflected light. And we look for what we call biomarkers, the evidence of chemistry that can only take place if there's some ongoing biological activity. In some cases, that would be, for example, methane. Cows on this planet produce an enormous amount of methane. So if there's another planet out there, a bovine planet that supports great amounts of cows, we might be able to see that. You have to rule out other explanations. For example, we're seeing methane being emitted from Mars, which is very exciting. It might signify that there is small microbial life under the surface of Mars, but it might also be caused by geological activity. There are methane reactants that are due to internal geological processes, and so scientists right now are trying to discern what is causing that methane coming from Mars. So you can't jump to the conclusion that it's life just because you see some of these biomarkers. Putting telescopes into space help, and this is sort of a graphic example of the difference between a very good ground-based telescope, in this case the view of the Eagle Nebula, and what we've been talking about last night and already this evening, the sharpness you get with a space telescope when you're above the atmosphere. So this is the Hubble Space Telescope image of that same Eagle Nebula, the columns. You get a much sharper image. We've talked about Hubble. I mentioned last night, sorry for those of you who missed it, but we got to go through the launch of the servicing mission that we did last May, where we sent the space shuttle up to the Hubble Space Telescope, and the astronauts were able to put in new cameras and new instruments for over several days of excellent work. And because of that, we're going to be able to study certain types of exoplanetary atmospheres with Hubble for the next few years. But Hubble's not the best telescope for exoplanet detection. It's good for certain kinds of atmospheric studies of transiting planets, but it's not the right kind of telescope for surveying for planets as small as the Earth. We need a different kind of telescope. So NASA is contemplating what kinds of telescopes that might be. We have ideas for space-based telescopes that would measure the astrometric wobble of stars very precisely. Such a mission is called the Space Interferometry Mission. It's one possibility. Another is to build a telescope that has a very good space-based coronagraph, so you might be able to take images and spectra of these planets right away. And we launched a telescope just this last year called Kepler. Kepler has a very specific capability. Kepler is designed to point to one cluster of bright stars. I think I've got it right here. Let me move on. We'll talk about Kepler in a few minutes. But Kepler stares at one series of bright stars and looks for transiting planets that would be orbiting some of those stars. I'll talk about that in just a minute. Here's the transit method. As I mentioned, the transit, you see a transit if you just happen to be random, these stars and planets can be in any random orientation relative to us, but some of them should be in such an orientation that that planet is orbiting along our line of sight. So here's the star that we're looking at, and there's the happy planet. You see it going in front of the star, waving at us, and it's blocking out some of the starlight. So as you see in the graph below the star, that total amount of starlight to us appears to drop a little bit when the planet is in front of it, blocking it. And then when the planet gets around to the other side, that total amount of starlight that we see pops back up again. Well, if we can't see the planet because it's too small, we can sometimes see that total amount of starlight dropping every time that planet orbits the sun. Now, it takes a while to see this because if you have an Earth-like planet orbiting a star like the sun, how long does it take for an Earth to orbit a sun? That's right. It takes 365 Earth days, more or less. So it takes a while to do this kind of analysis if you want to look for Earth, especially if you want to see several orbits to make sure you're seeing what you're seeing. It takes years. But we have this telescope Kepler that's designed to do just that. So right now it's operating in space. It is staring at a group of very bright stars. It's watching for how many of them have these periodic drops in their brightnesses, and it's determining from that the sort of statistics of how many stars typically have planetary systems and how many of them are Earth-sized planets. It has to extrapolate because it can only see those stars where those orbits happen to be along our line of sight, but you can do that sort of extrapolation to how many there must be in total by the number that you see. So there's an artist's conception of Kepler, looking at that transiting system up there in the upper left. It's only been up there a few months, but it's already starting to find transiting systems. So here are the first 5 transiting planets that Kepler has discovered. Kepler, by the way, is named after a famous scientist who helped us understand orbits, so it's appropriately named. And you can see from this artist's picture here what's going on. You can see the sizes of the star and relative planet there, and you can look at the dips, the curves in the middle, and that tells you the brightness of the star and then the relative drop in brightness when the planet transited in front of that star. And from the amount of drop, you can tell something about how big that transiting planet would be. Now, Kepler hasn't been up there long enough to see things like Earth that have full year orbits, so it's only seeing these planets that are very close to their star, because when a planet is close to the star, the orbital dynamics dictate that it will have to orbit very fast. So the closer something is to its parent star, the faster its orbit. These things are doing their entire year's orbit in a matter of days, of our days. So you can see the bottom line. We have orbits of 3.2 days and 3.5 days, 3.2 days, 4.9 days. Can you imagine having a whole year in a matter of a few days? That's what these systems are like. And they're probably incredibly hot as well. Here's a pictorial view of the relative sizes of these planets that Kepler has discovered. We say sizes because it's the size you can really tell by the transit. The actual determination of the mass would depend on the density of the planet. You have to do a little more work to get the density and therefore to determine the mass. But you can see how big they are compared to, say, Jupiter here on the right, which is our biggest planet in our solar system. And then, of course, Earth, the tiny little thing off to the right. So these are very big planets. They're not Earth-like planets, but they're the first ones that show us that Kepler is working. And Kepler should be able, over the next few years, to detect Earth-like planets. All of these are so far away in this distant cluster that we won't be able to do many follow-up studies on these things, but it will give us the first-time statistics of how common are planets. Astrometry, again, we look at the wobble of stars. And we hope a future space mission will help us to do that. And then, of course, blocking out the starlight. Here's our scientist again up here in the upper left, blocking out the starlight so that we can see the happy planet waving at us next to the star. And then we confirm some of these things with ground-based telescopes, seeing if we can actually see the star wobble. We also are studying how planets form. It's very interesting to us to understand how did those planets get there in the first place? How did our solar system get there? So one way we do that is to study the debris and the disks of dust and gas around young stars that are still there that eventually will be blown away. Debris disks are a hot topic for study right now, and we are seeing them in great measure. Here's what we think happens. We think stars form, as I mentioned, in clouds of dense gas, such as the Orion cloud there on the left. And then eventually you'll get a planetary system around some of those stars, as is indicated on the right. Well, how does that happen? It takes millions of years. And we first believe that gas giants form when this disk around the star still has a lot of gas, because remember the stars are formed out of gas. And then as that gas around that star eventually dissipates due to the stellar radiation, the stellar winds coming out and clearing it all out, we are left with just a highly preferential distribution of dust and heavier material. And they can coagulate and actually collide with each other and create a new generation of dust called debris. And that can form terrestrial planets, and then eventually the rest of the things that are not in planets get mostly cleared out, such as in our solar system. What can we see observationally along this timeline? We can observe these disks at different stages, what we call the Primordial Disk that's full of gas. I study that with radio telescopes using the Very Large Array in New Mexico. The Transitional Disk, as this disk gets older and the planets begin to form. And then the debris disk that may be left behind even while there's already planets still embedded in that disk. We see these disks in many young star systems. This is Hubble Space Telescope images of systems where you can see that dark lane, that's dust in these disk systems. It's blocking out the starlight, but you can actually tell that's the equatorial zone around the star as it's forming. And this ugly thing I mentioned in earlier talks is a ring around an actual star called Fomalhaut. That star has been blocked out by a coronagraph so that you can see the surrounding ring. And we already knew a few years ago that something was unusual about this system because this ring was offset from the position of the star. The center of the ring should have been on the center of the star if it's orbiting material, but the center of the ring was slightly offset. And it was also a very sharply defined ring of dust around the star. Both of these things are evidence of a potential planet. So we even had a press conference when I was at NASA headquarters announcing that this star system most likely had a planet around it that was forming this sharp ring, and that was also creating this sort of offset due to the dynamics of the center of that ring from the star. This was quite exciting, but we didn't actually see a planet. We just inferred it. And then a little bit later, by looking at the data in 2006 and going back and looking at that same source in archival data in 2004, we actually found the star. This was Paul Callis and his collaborators found the planet, I should say, buried in the ring. And you can see it represented down there in the lower right. It's the first time that we've actually taken a picture of a planet. So this is very exciting. This is brand new. This just came out last year. The first image of an extrasolar planet. At the same time, another system, the same day, the same week, I believe, was announced that another group had also imaged an extrasolar planetary system for the first time. So we're witnessing right now the first time we've actually taken direct images of extrasolar planets. You can see 3 of them in this picture. The star is blocked out by a special technique they've developed on a ground-based telescope, and the planets are orbiting. They've seen them actually go through several epochs of motion, so you can see that they actually are orbiting the star. How exciting. These are not Earth-like planets. They're large Jupiter-like things, but it's the first time in human history that we've been able to take pictures of extrasolar planets. In fact, this chart tells you sort of the number of extrasolar planets and the methods that have been used to find them. So if you look at the years down here, starting in the early 1990s and mid-1990s is when these detections really started to take hold. You can see how this has grown and grown and grown until 2009 we discovered 85 planets in 1 year. And the colors here represent these different techniques I mentioned to you. The blue is by far the most popular method, which is this Doppler shifting radial velocity method. But you also see the other methods there, this transiting method, astrometry, even now the dark imaging and some other more exotic means of finding planets. Microlensing is seeing how they distort light from background objects, and that's how you can tell there's a planet there, or even pulsar timing. So we have different techniques that are yielding a huge number of extrasolar planets now. I'm going to skip that, but most of these planets they're all larger than Earth. But we're getting down, I think the smallest one is about 5 Earth masses. We call it a super Earth. So we're getting down to these smaller mass objects, and we want to find out if there are Earth mass objects. We'll probably need a better space telescope to be able to do that within the next decade or two. All right, so that was your astronomy lesson for the evening. You can take a deep breath. You got all that? Okay. And now I want to move into the reflection stage on this. What does it mean? We're starting, it's not science fiction anymore. We're finding hundreds of planets. We're within a decade or two of finding out whether Earth-like planets are very common or very rare. What are we going to do with this information? What if we find out that habitability of planets is very common? What do we do if we actually find life? This will be very exciting. Are we, as human life on Earth, or even any life on Earth, are we significant or special, or are we just average? Or is this just a big accident that we're here? Are we, in any sense, unusual? So these are the questions that we can now, we almost now have to address. Before, they were questions of luxury, because we didn't even know if there were planets around other stars. Now these are questions that we as human beings are going to have to think about as we start actually studying extrasolar systems. How do our discoveries affect our view of ourselves? Well, first we have to think about what does it actually mean to be significant? Are you significant if you are rare, a rare diamond, something like that? Or are you significant if you are common? In other words, if life is rare, does that mean you're more significant, or does that mean you're an accident, so you're actually insignificant? You can look at that in different ways. Are you significant if you are unusual, or are you significant if you are central? Are you significant if you are long-lived, or is a short-lived phenomenon even more significant because you pay more attention to it? What's significant? Think about that a little bit. We had a very momentous time in our human history at the Copernican Revolution. We found out that Earth is not the center of the solar system, and of course now we know that the solar system is not the center of our galaxy, and the galaxy is not the center of the universe. In fact, you could call any of these things the center, but it's kind of relative to the other things. So there's not such a concept anymore, and in fact we're now discussing the possibility of multiple universes. So if we're not the central, does that mean that we are completely dethroned from our favored position, and does that change everything about our theology of the importance of humanity? Some people think so. You've probably heard that, as I have many times, the way this is discussed. But we have to be careful about that too, because interpretations of position and its relation to significance vary as well over time. I heard a very interesting lecture by a professor from the University of British Columbia who studied the literature of Copernican times and found out that at that time actually being removed from the center of a certain cosmology was not necessarily considered a demotion in importance, but rather an elevation. At that time, the center was considered the bad place. Hell was down and heaven was up. And so to be removed from the center at that time, in much of the literature of that time, was considered an advancement. So, as we sort of read our own philosophy back into historical times, we have to be a little careful how we interpret what centrality and significance mean relative to one another. What does it mean? I wanted to refer to the namesake of this lecture series, Blaise Pascal, a famous, brilliant person from the 17th century who did much thinking in the realms of science and philosophy, and was a devoutly religious person as well. But he thought so deeply that he troubled himself. So some of you may be like that. You think too deeply. And he thought very deeply about the significance of his life. And it was, in some sense, his view, his wonderful understanding of the cosmos and the universe, and even the very minutiae of the small parts of nature that got him thinking about, what is the significance of humanity. He looked at the wonders of the universe. He imagined that the cosmos was infinite. And when he thought about this infinity, he not only was uplifted by thinking about it, but it also kind of depressed him, because he also felt that there were innumerable universes, if you will, on the small scale too. And of course, we now know with all of our studies of human atoms, human cells and atoms and subatomic structure, that it is true that there are, in a sense, worlds and universes down at scales smaller than we would ever have imagined before. So in some sense, he was foreseeing what we are seeing now using our nanotechnology and these kinds of things, and our telescopes seeing the magnitude of the universe, this huge span of size scales of things, and each size scale has its own sort of sense of a world of that scale, and it began to make him think more deeply. And in fact, he said, what exactly is man in nature? When you think of this infinite cosmos, he said, man is a nothing in comparison with the infinite. And then when he thought of this smaller scale, sub-visible world, he called that the nothing, because it would get smaller and smaller. And he said, we are an all in comparison with that nothing. We're a mean between nothing and everything. And you should read his entire essay on these topics to get a fuller understanding of where he was going. But I think he made himself depressed, because he said, he's also considering this span of time. And he said, when I consider the short duration of my life, swallowed up in the eternity before and after, the little space which I fill, engulfed in the infinite immensity of spaces of which I am ignorant, and which know me not, I'm frightened. And I'm astonished at being here rather than there, for there's no reason why here rather than there. Why not rather than? I didn't get that quite right. Why not rather than then? Why not then or now? Who has put me here? By whose order and direction have this place and time been allotted to me? He's trying to figure out, why am I here in this place right now? The eternal silence of these infinite spaces frightens me. So here we are on our little space, and we might find other life. What does that mean? Are we significant? All right, these are my personal musings on the topic, and I would like to say that the answer is definitely no and yes. No, we're not significant. We don't seem to occupy a special place or a significant volume in our own galaxy or in the universe. It seems that planets are common, and we may even find that life is common. I don't know. Our lifespans are insignificant in relation to the time history of the universe. That would be a no. However, but our planet has evolved using these heavy elements produced over billions of years of star production. Our Earth is in just the right situation for sustained life to thrive. In fact, it seems like there are many other situations where the harsh realities of the cosmos would really not allow life to thrive in a sustained sense. Advanced life, like ours, may, for that reason, be uncommon. And in fact, the fundamental constants that govern the entire universe seem to us to be finely tuned to allow stable development of life, at least in this universe, and at least on this planet. Why is that? Small tweaks in these things would not have allowed the time frame and the structure formation that we need for life to thrive. It does seem that, in fact, there is something significant about our being here. But you can go back to no again. There might be other kinds of life, and there might be other universes that have other fundamental constants. And so, yes, by definition, we're here and we mesh well with the conditions in this universe, but that's kind of by definition. There may be plenty of other universes that have different conditions, and we're just a cosmic accident, if that is the case. However, but, here I go on the yes again, regardless of our particular place in space and time, why has at least this universe allowed the development of inhabitants in at least one place who study the universe, who consider their own destiny, who have lectures like we're having tonight? What's the purpose of this? It almost does seem that there's some significance to our existence by the very fact that we can think about our existence. In fact, what if, muse with me for a moment, what if the universe, or if you think there might be others, universes, what if the universe seems to be infused with a physical potential from the very beginning, such that the development of life in some form, complex thinking life that can study the universe and even have a spiritual perception, was bound to come forth somewhere, sometime? What if we were meant to be? It sometimes seems to me that our universe was infused with that potential, and that with the patience of time, life was bound to emerge at some point. Now, this is beyond science. Science measures physical forces of nature and cause and effect of these physical forces of nature, measuring material things we can measure. Science can't answer these bigger questions of, is there a spiritual realm? Is there a divine purpose? So this is not a scientific question, but we can ask, why are there intelligent beings in this universe who recognize the universe and who recognize concepts like pain and joy, or recognize that there really are realities of good and evil? Why is this? It does seem to me that there is some sort of infusing of purpose within this universe. Now, these are the lectures on Christianity in the universe. So if we look into biblical scriptures, where does our significance come from in terms of biblical revelation? And in biblical revelation, it is also true that our significance does not come because of our lifespan or because of our particular position. In fact, we are told that we're dust. So there goes that sense of pride. We are not significant because of our place, our lifespan, but in biblical terminology, it's because of God's choice to love us, to call us, to redeem us, to be with us. It's the choice of our Creator, that God knows each person, actually converses with us in prayer. This is not a distant God, but a personal God. Hates evil, loves good, forgives sin, and gives eternal life. This is the kind of God that's described in biblical Scripture. It's a God who is a person, who has a sense of relationship with created beings. And Psalm 103 says, as a father has compassion on his children, so the Lord has compassion on those who fear or revere him. For he knows how we are formed. He remembers that we're dust. In fact, we are in fact stardust. As for man, his days are like grass, but from everlasting to everlasting, the Lord's love is with those who fear or respect him. Praise the Lord, all his works everywhere in his dominion. So the thought is it possible that the magnitude of time and space in this universe was God's way of developing and providing just what we need for life and for eventually recognizing God and maybe even seeking a relationship with our Creator? A thought. We're not the first ones to think about our significance in terms of looking at the universe. In fact, King David wrote about this. And remember that King David wasn't always a king. He was a shepherd boy. He had lots of time out with the sheep where it was very dark and he could see the stars night after night after night. And he had a lot of time to look up and think of them. That's one thing I think people miss today, is not being able to see the sky at night and being able to contemplate the beauty of the heavens. And he wrote later on, as he wrote poems and songs, he wrote, "O Lord, our sovereign, how majestic is your name in all the earth. When I think about your heavens, the work of your fingers, the moon and the stars which you've established, what are human beings that you're mindful of them, or mortals that you care for them?" What is our significance? But then he went on and recognized, he said, yet you made them a little lower than God and crowned them with glory and honor. So for some reason, even though our position in time and space is rather insignificant, we have been given a sense of, if you will call it, glory. We can contemplate our existence. And in fact, we do have dominion over our own planet, for good or for ill. We have the ability to do great good with this planet or to cause great trouble, but we do have that kind of power over our own planet. All right. Some of you may be saying, how can you possibly believe in God in an age of scientific understanding of the universe, and also when there's so much suffering and hypocrisy and all kinds of things? And these are good questions. And so I just want to throw out some helpful references if you're struggling with this. Many people have been helped by the books of C.S. Lewis, such as Mere Christianity. And Sir John Polkinghorne, a physicist who later in life became an Anglican priest, has written a whole slew of very good and helpful books on how to relate scientific views of our world with theological views, such as science and providence. And then, as I mentioned last night, a great book by Francis Collins, who is a geneticist and understands the development of the human DNA over time, has written a great book called The Language of God. He became a believer as an adult scientist, and he writes about what brought him to that belief. And then there are books such as Perspectives on an Evolving Creation, which has chapters on different topics of science and biblical interpretation. Editor for that is Keith Miller, and I wrote a chapter in that book on astronomy and cosmology. I'm a co-author with Deborah Harsmith, so I recommend it. And of course, the scriptures themselves are helpful. All right, what about specifically Christian thought, however? This is a really interesting direction to go, because these are the lectures on Christianity in the university. So what is it that's, might be specific to Christian thought? And Christian thought is focused on the person of Jesus Christ. What does this have to do with what we're talking about tonight? So you could ask the question, if we found an alien civilization, would they in fact experience any presence or redemption of God in person, as we believe in Christian thought was done on this planet through the coming of Jesus Christ, the Word of God made flesh, becoming part of creation? And in fact, there are many verses that you might extrapolate to this effect, such as 1 John 2:2, that says Jesus Christ, the righteous one, is the atoning sacrifice for our sins. His death covered the penalty that we should pay for our sins. He was raised again. And it says not only for ours, but also for the sins of the whole world. Well, what if the whole world could include other places, other civilizations, other planets? Could you extrapolate Christian theology to other worlds, other civilizations, or would that cause a great crisis of faith if we were to discover other intelligent civilizations, especially ones that had a very different theology? So this is the kind of thing that can create great dinner conversations. And if you want to test it, I did tonight. So I was having dinner with a group of faculty here tonight. Many of them or all of them from some sort of Christian denominational background. And we were all talking about the normal things that you talk about over dinner. And I said, this won't do. I really want to throw out the question that I'm going to talk about tonight. And I said, let's suppose that we find intelligent alien life. Would they, within the rubric of Christian faith, would they need redemption the same way we believe humans do? And would God have visited them in the same way that God has visited us? And would what Jesus did for us cover them, or would Jesus have to come in the form of the alien life to teach them and to redeem them? So would this Savior come in a form that looks very different from us? Whoa, this started a conversation around the table that I wish would have continued, I think, for hours had we had enough time. And there were many different points of view on this, that this either, is an issue that we should leave in God's hand and not worry about, or that we should really take very seriously, that it would be a real challenge to us if we found another civilization that perhaps was more righteous than us and had no Savior. What does that mean? So we thought about that a lot. So we didn't come to any conclusions, but it does bring to mind that finding alien life may or may not pose theological challenges I tend to think that what we find in Scripture in terms of Christian theology is that anything or any life form we would find out there would be under the umbrella of God's care and providence, and it would be a marvelous discovery. But it does make you think. I'm going to close with this exciting quote from Thomas Wright of Durham. In the 18th century, was thinking about an idea that was mentioned in Paradise Lost, the idea of many suns. And he thought, what does that mean, many suns? What would it mean if there were, in fact, many things like our sun? And so he started doing this little mental calculation. And he said, now, admitting the breadth of the Via Láctea, or the Milky Way, to be at about a mean 9 degrees, so he's doing this little math. It's like his back-of-the-envelope calculation here. And supposing only 1,200 stars in every square degree, let's do that math, there will be nearly in this whole area about 3,888,000 stars, and all these are just a very minute portion of this great expanse of heaven if you extrapolate. Whoa, this hits him hard. He says, wow, what a vast idea of endless beings must this produce and generate in our minds if these stars are all suns like our own solar system. And when we consider them all as flaming suns, as progenitors, prima mobilis of a still much greater number of people's worlds. Okay, so now he's talking about inhabited worlds. What less than an infinity could circumscribe them? What less than an eternity comprehend them? What less than omnipotence produce and support them? And where can our wonder cease? I like that. I think that's the excitement that we need to have as we contemplate the search for extrasolar planets, life, and our place in this most amazing cosmos which we inhabit. These are more resources that I mentioned last night, in particular the Canadian Christians in Science in the UK and the Canadian Scientific and Christian Affiliation, which I don't have on this chart. I'm going to close by saying that I have another gift for you. These are more pictures from the Hubble Space Telescope. It's the galaxy picture here on the right that I have copies of for you tonight. The Whirlpool Galaxy. I wish I had pictures of extrasolar planets for you to go with the theme, but I don't have it. So after the lecture tonight, you can come up and have a picture of this galaxy pair, and it tells you about it on the back. And if you're really nice to me and say something nice about the lecture, I'll give you a sticker about the Hubble Space Telescope servicing mission and 15th anniversary of the telescope. So that's my ending slide. I thank you all tonight for coming and taking this little journey of philosophy and astronomy with me, and I would be happy to answer any questions. Thank you.
So if we could perhaps have the lights up a little bit to see, then as Jennifer said, she would be happy to take questions, and just raise your hand and we'll get to you. Over there we have a question.
Yes.
Dr. Wiseman, you touched on something earlier that really hit home with me, and that was, if in our search for exoplanets we were to discover an intelligent species, and if that species had a divine purpose, isn't that the answer to the question that we all seem to be striving for, our belief in this, and in itself, that discovery of another species that believed in a divine intervention, isn't that in itself possibly the answer to the question that everybody seems to have been searching for?
Well, it depends on what, you could imagine all sorts of scenarios, right? What if you find another, we might just find bacterial life on other planets. So would that really challenge our theology? I think we could work through that pretty easily by saying that, since God has enabled this life to be very fruitful, this planet to be very fruitful in life, that maybe it still might cause problems for some people, but for me, I think I could imagine that this whole fruitful universe could produce life. But if you get to this point of intelligent civilizations, what if they are, we discussed this over dinner, what if they do have a sense of the divine and so forth that kind of parallels ours? That would be a kind of a confirmation. What if they, in fact, look at us as lower life forms and treat us as pets, or or what if they have no concept of good and evil, or what if you could imagine all sorts of what ifs, and but I do have to think that Christian theology is robust enough that whatever kinds of civilizations we find, we might have to do a little bit of recalibration of where we fit into the whole scenario. But it's all going to fit into this bigger picture of divine care and oversight. I think of sort of a parallel when people on this planet, explorers from one continent, would discover, if you will, a people group on another continent that they didn't know about before. They had to many times go through a crisis of understanding, are these people groups, are they the same as my people group, or are they somehow lesser than human or superhuman or what? They had to kind of figure that out. So it might be a magnified experience of that if we were to encounter some alien civilization. But I think you're right. If we found that they sort of fit within this rubric in a larger sense, that it would be a confirmation of our who knows? So, yeah.
Other questions?
More questions?
Yeah,
yes.
Up there.
There are some science fiction writers who've addressed some of these issues about aliens and their religious beliefs. I'm thinking years ago, James Bliss did a book called Case of Conscience, where he speculates about another planet, whether or not there's good and evil, and can there be just natural goodness without some kind of revelation. And more recently, a Canadian writer, Robert Sawyer, has a book called Calculating God, where aliens visit the Earth, aliens who are believers, as it were, in the existence of a deity. And finally, just last remark, Ray Bradbury did a poem called Christus Apollo, where he speculates about Christ becoming incarnate on other planets.
Interesting.
Maybe things you might be able to refer.
Christus Apollo.
Yes.
Very interesting. Ray Bradbury writing a book about Christ visiting other planets. Is that?
Well, it's a long, very interesting
poem. It's a poem. Very good. Okay, very good. Thank you for sharing that. Of course, there's also the issue of what if we search and search these hundreds of billions of planets. It's very hard. It's almost impossible to prove a negative. But what if we find that there's no evidence of life anywhere, and that there really isn't any evidence that any other planet is hospitable for any kind of life that we could possibly imagine? What do we do with that? Why would there be such an enormous universe with countless galaxies and stars and life in only one place? And some people are comfortable with that theology that shows a specialness for our life here that fits in with their sort of view of God. Others, that's not a very satisfying thing. You would like to think that this creative God has embellished, made an abundant and extravagant universe with life everywhere. So I think not finding life is also as challenging as finding life in some sense to contemplate. Yes.
I have on the topic of proving a negative.
Yes.
One of the things that strikes me is that it seems like there's really faint. You're working with very faint data in finding these exoplanets. Do you have any ways to determine that a star does not have any of these planets? Because it seems like there's sort of the possibility that it looks like there might be a planet here, but the data is so faint, and I don't know how you sort of.
You can tell if it's a particular kind of star, so that you can do these kinds of studies. You can tell, for example, if it's not wobbling. If you detect no stellar wobble, then you can tell that there's no planet bigger than a certain upper limit in mass, depending on your detection limit. So you could tell in that sense that there's no planet bigger than your detectability limits, so that there'd be no larger. Many of these stars have been looked at, and no planets have been found. But all they can say is that no planet smaller than, say, 1 Jupiter mass exists around that star. But we don't have the capability yet of detecting something smaller than that. Now that limit is dropping and dropping because our technology is getting better and better. So you can affirm in these particular types of stars where you can do these kinds of tests, you can affirm that there's no planet larger than a certain size. Yeah.
As we begin to find planets that are Earth-like and that may possibly contain life, what is our plan for attempting communication?
Okay. Well, again, you have different types of researchers. So most, like the scientists in my lab, if you found a planet that looked even possibly habitable, like it's at the right distance from its parent star, and it might be small enough to have a solid surface or something like that, the first thing you really want to do is do spectroscopy and try to see if you can find evidence of biological activity. Could there even be things like plants, this kind of thing. And so most scientists would be concentrating on looking for simple life, but I'm sure if such a habitable planet was found that the SETI folks would immediately turn their antennas toward that system and start listening really hard. In terms of actually transmitting, though, I don't know of anybody that's actually we are unintentionally transmitting all kinds of signals, because many of at least when we'd had analog television, many of those signals are being radiated off into space. So many of our communications and so forth are unintended signals that are heralding our presence to the universe, which can explain why we're not visited by intelligent civilizations, because they see what they're getting into. So I don't know of a specific plan for making contact if we were to find, but I'm sure that if we were to find a planet that looked like it might truly be habitable, if not inhabited, there will be a lot of new attention on questions like that. So,
Okay, we have time maybe for 1 or 2 more.
Remember that there's also a light travel time problem. So even our nearest star, Proxima Centauri, is 4 light years away. So to do a round-trip conversation takes 8 years at least. And many of the nearest stars are hundreds of light years away. That's our nearest neighbors. So the likelihood of finding a star that's within the realm that within a human lifetime you could have a back-and-forth conversation is highly unlikely, actually. Yes?
So my question, how far away in light years is the average planet being found right now?
Well, these are a range of probably in the order of 50 to 200 light years away kind of thing. So they're near enough that you can do these detailed studies, but they're far enough that it would be very difficult to have an extended two-way conversation with these creatures. Yes.
Yep.
Are all of the exoplanets that have currently been discovered within our galaxy?
Yes, right. And the simple reason for that is that it's very, very hard to do these detections. So you're looking at the nearest things for the most part that you can examine first. And so these are not only within our galaxy, but they're within our tiny little region right around our little spot in one spiral arm, with the exception of this field that Kepler telescope is looking at when it's looking at a whole bunch of stars to try to all at once and staring at them to find if there are any planets. It's looking at a little bit farther out, still within our own galaxy, but they wanted to find a region that had a dense cluster of stars so you could watch a whole bunch of stars at once. And that's also a downside, because if it finds, and it should find, a statistical sample of planets, it already is, but these stars are so far away that to do follow-up spectroscopy, which is what you'd really like to do, study the atmospheres of these planets, they're too far away to do a really detailed study of follow-up. So that's the downside.
Okay, one last question.
Is
Yeah.
it known what percentage of stars could support planets?
That's exactly what Kepler is doing those statistics. We don't know. But the Kepler mission, by looking at a large number of stars and figuring out the statistics of how many of them have these planetary systems it will help us more. With the small number of statistics that we have, it looks like that not every star has a giant planet around it, but that it also appears that our own configuration of planets might be somewhat unusual in that we have the small terrestrial planets on the inside, and then we have the big gas giants on the outside of the solar system. But we're seeing quite a few of these systems that have huge gas giant planets very near their parent star, and that might wipe out any chance of having a terrestrial planet in its habitable zone. So, we don't yet know, but we may, in a few years, after Kepler does its thing, understand whether our solar system arrangement is unusual or is common, and we'll have better statistics on that.
Well, thank you for your questions, and as you heard earlier, Jennifer has a gift for you. You can come down and get it, but Jennifer, we have a gift for you.
Oh, well, okay.
We would like to thank you very much for delivering these Pascal lectures here, one last night, one this morning, and the one this evening. This is a book that we hope you enjoy that will commemorate your stay here at Waterloo. And I would like all of us to give Jennifer a big round of applause for time with us. We have, as I said, cookies and juice out there so you can continue discussion. Please come down here and avail yourself of these pictures from the Hubble Space Telescope, and I think Jennifer might be willing to discuss privately with people some other issues if they'd like. Thank you all for coming out. Good evening.